feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we continue our discussion on radical functions, graphs, and now today's solutions. So let's jump right into some content here. We are going to continue pushing into radical function and actually looking at solving radical equations. So this might be a newish concept to you guys here. When we solve radical equations, we're going to follow a similar process that we have done in most instances other than factoring this year, where we follow reverse order of operations or SADMAP to get to a solution. Now, there are some key things to note here and some techniques that we're going to apply and use that's going to help us to solve these equations. Following through the ideas of inverse operations, we'll see three properties. So if we're given A, B, R, and S that are real valued expressions, so we're working with real numbers here, not imaginary numbers. If the rth root of A is equal to B, then A is equal B to the R power. Essentially what we're doing here, again, is focusing on the use of inverse operations. So if I have the rth root of A equal to B, and I want to get rid of that rth root, I would take A to the rth power, to the power of R. And then if I do that to the left, if I take A to the power of R, I have to take B to the power of R. Well, the rth root of A to the R power simplify each other because that can be rewritten as A to the R over R power, which is just 1. Oops, sorry there. So that's how we get from the expression here on the left to the expression on the right. We're going to kind of use that idea, that inverse operations, to create some shortcuts while solving. Now, that's if we're just dealing with roots. What if we mix roots with powers? Well, then we can go ahead and write them into a rational exponential form. So there's two different scenarios that we may encounter. If S is odd and if S is even, we have to pay attention to S, which you'll notice here. S is the numerator in the exponent of A. So if we have A to the S over R power, and that's equal to B, then A is equal to B to the R over S power. Again, what we're thinking about here is trying to use inverse operations. So if I have A to the S over R power, I'm going to take that to the R over S power because that's the same as getting A to the R times S over R times S, which would just be A to the first power. Now if I take A to the S over R power to the R over S power, I have to take B to the R over S power. Now the same thing holds true in the third example, but the reason that we need this plus or minus here, remember, if S is even, S becomes a root, an index root. So let's just say if this was, A to the 2/3 power equals B, then we're having A equals B to the 3/2 power. The reason we need that plus or minus there is because we're writing essentially B cubed to the square root power, and we're creating that square root in the solving process. So when we create a square root in the solving process, we need to account for both positive and negative options that could give us the solution here. Okay, so that's going to be something that we're going to talk about, we're going to focus on and try to remember when we start to deal with rational exponents. Now, let's take a look at some examples. So in 3, it says find algebraic solutions for each of the following equations. Again, as I mentioned, we're going to follow reverse order of operations, or SADMAP. What we need to do here is take care of roots, which are another way of writing exponents. So that would be the E in the reverse order of operations. PEMDAS is simplifying. SADMAP can be used to solve. So the first thing that we want to do here in 3A is to subtract or add. But some people might look at this and say, okay, let's subtract 3. But remember that a root implies parentheses. So technically that plus 3 is already in some parentheses. So we cannot get inside of that root yet until we get rid of the root. So there's no addition or subtraction I can do to start this problem off in 3A. what I have to move to is division or multiplication. So I'm going to divide both sides by 2 here. If I divide both sides by 2, that leaves me with the root of x plus 3 equal to -4. Again, just dividing both sides by 2. Now I can get rid of the square root. Now we have solved problems like, let's say, x squared equals 4. We've solved that by taking the inverse operation and square rooting to get plus or minus 2. Well, if I have a square root, the inverse of the inverse operation would be to square both sides. And as we have in the property written above, if I square both sides, what I'm going to be left with is the radicand on the left, x plus 3, and -4 to the power or the index of my root, which, remember, a square root, if no number is written there, the power is 2. The index is 2. So this would be x plus 3 to the -4 to the second power, which is the same as x plus 3 equals 16. Now I can subtract 3 from both sides and get x equals 13. And we can check this in our graphing calculator if we'd like. Let's get out of that graph from last video and take -2 times the square root of 13 plus 3. And we'll see that that equals -8. I made a mistake here. Aha, sorry, I did not make a mistake. What we have to do is I almost forgot to mention this. What we have to do when we go through the solving process is we have to check for extraneous solutions. So sometimes when we create quadratics in the solving process, and we created a quadratic here, it's going to give us 2 potential options. One of those options could be true, and one of those options could be false. So if I go here and I take this x equals 13 and I substitute it back in and it comes out as -8, this is actually not a solution. This is what we would call an extraneous solution. So to this problem, we have no solution. Now what I can do is to check this graphically. Remember, you learned this in Algebra 1. If I want to solve an equation graphically, so let's type in the left side of the equation, -2 times the square root of x plus 3, and that's equal to an 8. I'm looking for an intersection of those 2 graphs. Well, if I take a look at this graph over here to the left, it's a reflection, so it's going to open going down. It's never going to intersect 8. So this actually does have no solution. So part of the process that we're going to have to do here with solving radical equations is check our answers and look for extraneous solutions. In this case, x equals 13 is extraneous, and there is no solution. So let's go ahead and take a look at B and see if there's a solution for B. Now notice that there are 2 x's here in this equation. There's an x inside the square root, and there's an x outside the square root. We do want to combine those, but remember, I cannot get into the square root until I get rid of the square root. So I have to move everything else away first before I can get to this square root. So I'm going to follow SADMAP. I'm going to try to get the root by itself. I'm going to subtract 12 to start. So subtract 12 from both sides to get the root by itself. Then I can get rid of the root. So the root of 3x minus 2 would equal x minus 2. Now I can get rid of the square root by squaring both sides, which would leave me with the radicand 3x minus 2 equal to x minus 2 squared. So I'm going to have to do a little extra work here. I'm going to have to square out this x minus 2, which would be x squared minus 4x plus 4, using our rules there. Now I've created a quadratic equation, so I need to solve my quadratic equation. I can solve a quadratic equation by getting it set equal to 0. To do that, I need to subtract 3x from both sides, which would give me x squared minus 7x. I need to add 2 to both sides, which would give me a positive 6 over here on the right. Now I can solve this a variety of different ways, but this is a quick factorization. So I can go ahead and factor this into x minus 6 and x minus 1. So x minus 6 times x minus 1, if I check that, this would give me negative 6x. This would give me negative x. That adds together to give me negative 7x. Negative 6 and negative 1 are factors of positive 6. X and x is factors of x squared. To solve, I set both factors equal to 0. X minus 6 equals 0. X minus 1 equals 0. And I get the solutions 6 and 1. But first, let's check for extraneous solutions. So I'm going to go back to the beginning of this equation, and I'm going to take 3 times 6 minus 2 inside the root plus 12 outside the root, and make sure that should be x plus 6 or 16. 6 plus 10 would be 16, and it is. So the left side of the equation, if x is equal to 6, is 16, and so is the right side. If x is equal to 1, if I would have put a 1 in over here on the right, this would be 11. So I need the left side of the equation also to be equal to 11 when x is 1. This time, if I put in 1, I'd find out that the left side of the equation would be 13 while the right side is 1. So this is not going to be a solution. So we can check those extraneous solutions. You can write the substitutions out and simplify if you would like to, but we can check those extraneous solutions on the calculator like we did here and find out that 6 is not a solution and 1 is going to be 1. Let's go ahead and take a look at a different example using a different type of root. So in problem number 3, we have a cubed root this time. We're still going to follow the same type of process here. So when we solve, we're going to subtract 8 from both sides. So we get 2 times the cubed root of x minus 5 equal to negative 12. Then we're going to divide both sides by 2. So we get the cubed root of x minus 5 equal to negative 6. Now this time when I get rid of the cubed root, the radicand x minus 5 is left on the left side. Now I'm going to have on the right side the negative 6 to the third power. So when I use that first property we wrote down there at the beginning here for solving radical functions, notice that the index of the root becomes the power of the constant or the expression on the other side of the equation. So if you know negative 6 to the third power, that's excellent. If you don't, we can do that in the calculator real quick and find out that negative 6 to the third power is 216. So x minus 5 equals negative 216. Add 5 to both sides, so we get x equals negative 211. And let's check this before I circle it. Let's go ahead and check this for an extraneous solution. Make sure this is the solution. So 2 times the third root of negative 211 minus 5 inside the root plus 8 outside the root should be negative 4, and it is. So we have the correct solution here. Let's go ahead and take a look at some more examples as we start to increase probably the difficulty here. Taking a look at D, what we notice is we have 2 roots in this case. Now, when you have 2 roots, we can still follow the same process. What I would do first in this instance is I would get one of the roots, I would get the roots to be on different sides of the equation. So I'm going to leave the root of x plus 15 on the left side of the equation. I'm going to add the root of x plus 3 to the other side to get 2 plus root x plus 3. Now, you do not have to do this, but what we're going to try to do is get rid of the roots. And in order to do that, we want to get to our property that we wrote down here, which has a root of radical expression by itself. So if I can get the root of x plus 15 by itself, now I can square both sides to get rid of my first root. So remembering our property from squaring binomials, you square the first term, so 2 squared would be 4. Then you take the 2 terms, these two terms, you multiply them together and double that. So that would be 4 roots of x plus 3. Then you square the last term. So the square of the square root of x plus 3 would just give me plus x plus 3. Now I can combine some terms here, move some terms around. So I'm actually going to write out this step. I'm going to subtract x from both sides. I'm going to subtract negative 4 from both sides, and I'm going to subtract 3 from both sides. The reason that I'm doing this is I want to get now this root by itself. So I get a lot of things that cancel out here, or subtract out to give me 0. And I end up with 8 equals 4 root x plus 3. Now I need to get rid of that 4 inside of my other root, so notice that this simplifies kind of nicely, and now I'm left with just a single root. So this takes a few steps here, but if I move one root to the other side of the equation and then I square both sides, now I can get down to a single root. Now again, I can square both sides, so I'd have 2 squared equals x plus 3. 2 squared is the same as 4. And then subtract 3 from both sides and get 1. Let's make sure this is a solution. So I'm going to take the square root of 1 plus 15 would be 16, minus the square root of 1 plus 3 would be 4. And I would get 2. So 2 equals 2. Therefore, x equals 1 is a solution. So if you have two roots combined into one equation, move one root to the other side, so they're you isolate one, get rid of your first root, and then after simplifying the other side of the equation, work on getting rid of your second root. Now let's take a look at an example here where we're actually kind of gone away from roots, and now we're writing with rational exponents. So any root can be written as a rational exponent, but when we work with rational exponents, we need to remember this property. So if s is odd, when we get rid of our rational exponent, or essentially move our rational exponent, then we only have to deal with one case. But if s is even, we have two cases where we have the plus or minus in front of our constant on the other side, or our real valued expression on the other side. So let's take a look at 3 then. So if I have to solve here in E, the first thing that I'm going to do is try to get to this parentheses or this exponent expression by itself. So I'm going to divide both sides by 3. So this leaves me with x minus 1 to the 2/3 power, and that's going to equal 3. Now again, essentially what I do here, and you don't necessarily need to show this step because we have that property, is I'd take the 3/2 power of both sides. So if I take a 3/2 power of both sides, I'm going to get x minus 1 equals 3 to the 3/2 power. Now notice that, again, my numerator was even. Now that becomes my denominator, which is the radical expression for the root. I need to take a plus or minus here. Now you'll see why as I rewrite this. So I'm going to go a little bit further, and to go a little bit further, I'm going to rewrite this into root form. So x minus 1, you don't necessarily have to if you can simplify this, would be plus or minus the square root. The index would be 2 because that's our denominator here, of 3 to the 3rd power. So x minus 1 equals plus or minus the square root of 3 squared times 3. We can rewrite that. So x minus 1 equals plus or minus 3 root 3. Then I can add 1 to both sides. So x equals 1 plus or minus 3 root 3. So I simplified that radical expression just by dealing with the exponents. If you wanted to simplify that radical expression, you could have rewritten this as plus or minus root 27, broke that into plus or minus root 9 times 3, which square root of 9 is 3, so plus or minus 3 root 3. So again, we have to have that plus or minus out in front because it became a radical expression when we went through our steps of simplifying. So we can check this. We can check this to see if this is correct. So 3 times the quantity 1 plus 3 root 3 minus 1. Sorry, that minus 1 should be outside of that radical expression. So minus 1 to the 2/3 power, and this should equal 9. And it does. We can take this same expression, and because it's plus or minus, put a minus in front of that 3 root 3. And we see that it equals 9, so we do get the correct expression here. Okay, so here we're getting rid of that exponent by using the third property that we had. Let's take a look at f. Again, the goal is to get the exponential function, or the exponent by itself, and then you can get rid of that exponent. So those parentheses with the exponent of 3/4, we need to get rid of that. So in order to get rid of that, we have to move the other pieces. First, we're going to subtract by 6. So we get negative 1/2 x plus 1 to the 3/4 equals negative 4. Then I multiply both sides by a negative 2. So I get x plus 1 equals positive 8. X plus 1 to the 3/4, excuse me. Now I need to get rid of that exponent, so I'm going to use my property. X plus 1, what's left in the parentheses, essentially the radicand would be left over. And this would become 8 to the 4/3 power. 4/3 is the same as, and you don't have to do this, but you can. 4/3 is the same as writing the cubed root of 8 to the 4th power. You can also do that in your calculator. The cubed root of 8 is 2, and 2 to the 4th power is 16. So now we can subtract 1, and x equals 15 would be our final solution. Now notice in this case, I did not put the plus or minus when I got rid of my rational exponent. I did not put the plus or minus because the resulting index is an odd number. And in that case, we don't have to worry about positive and negative cases. Odd index powers take care of both. Again, we could check this by typing this into the calculator, and you would find out that this is the actual solution. This is a good place to stop. So here we have developed some properties and some techniques for solving radical equations and equations with rational exponents. As always, thank you guys for tuning in, and I'll see you soon.